huge pleasure to be back in Vienna. I was first here 10 years ago, and I've come back many times since, and it's my favorite place to do math, honestly, in the world. So I'm thrilled to be here. Thanks to the organizers for inviting me. I am going to start off with a motivating example from 2D fluids. It's going to be a little bit technical, and I apologize for that, but it's basically to see what sort of things we want from the geometry of diffeomorphism groups and how they can help us prove other sorts of theorems. So one of the things I always get asked if I give a geometry sort of talk at a fluid mechanics conference is, how does this help us prove anything that we actually care about? Because they don't care about just putting geometric structures because they're pretty. I care. I mean, I don't have to convince you of that. That's beautiful, and we love that. But we also want to prove some theorems that are harder from the PDE point of view and easier from the geometric point of view. We'll start off with the Euler equations for a 2D incompressible fluid. Euler derived these in the 1750s. Only the second PDE ever done after the wave equation. So kind of interesting that we still study it and it's still so difficult now. So we'll start with fluid particles in the plane following some trajectory. I'm going to use capital X and capital Y for the sake of classical notation. And the only real assumption that we have to make is that, number one, it's incompressible, and number two, the fluid moves subject to some potential energy, which we call the pressure, and the fluid basically invents its own pressure in order to make itself stay incompressible. So these would be the equations just for the general potential energy. I'll abbreviate it as capital XTT equals minus px of capital X and Y. Those are functions of little x and y. And the incompressibility constraint is that the determinants of the gamma, which is the diffeomorphism that moves the particles around, that determinant should always be 1. And so what this tells you is the fundamental variables in this system are the partial derivatives x sub x, y sub y, etc., not so much the particle paths themselves. I need to work with the partial derivatives. They need to make sense. So if we differentiate these equations with respect to x and y, we get a 2x2 system, just using the chain rule on these. And I would like to view this as a nice system for continuous functions, capital X sub x, capital X sub y, etc. If I differentiate the constraint in time, I get, obviously, by the product rule, something like this, which doesn't help me quite yet. But in principle, if I forgot about the particle trajectories themselves and just knew the partials, I could reconstruct the whole diffeomorphism. So I'm going to try and view everything just in terms of these partial derivatives. And I differentiate the constraint in time again. How much time do I have? Okay, I'm running short on time, so I'm going to skip some of these. Little technical. I wasn't sure if that joke would work, but I worked really hard on it. Okay, so the system we actually want, if we, once we write everything just in terms of the partials, we get this big system for the 4 partial derivatives and their 4 time derivatives in terms of the same things, and some big matrix in terms of the pressure Hessian, the second derivatives. And the pressure solves the Laplace equation, so you are probably familiar with this in the Eulerian form, but this is the Lagrangian form of it. So if I know these things, all these partial derivatives, I should be able to reconstruct the pressure from the Laplacian, and if I can reconstruct the pressure, then I can reconstruct the full Hessian. And so this is supposed to look like a system omega for omega of t, which is, so omega is a bunch of continuous functions of space. And I like working with continuous functions because I don't need to get really into details of function spaces, just continuous functions. Everyone understands that. You teach that to your basic undergrads in an analysis course. So if I can view things in terms of just continuous functions, it's the easiest infinite dimensional example. So what I want is, if this is a nice continuous function of all these things, then this is an ordinary differential equation, and I know how to solve an ordinary differential equation. There's only one theorem in the entire field of ODE, which tells you how to solve it, which is do Picard iteration. So I take this thing, I integrate both sides in time, and I consider this as a fixed point iteration, and I hope it converges. So standard theory says it's a contraction mapping as long as this f is a locally Lipschitz function, which in normal cases it would be. And so I should get a solution for at least small time. And I was actually expecting someone would object to this. But no, so I'm glad I didn't write that in. Okay, so this is false. Of course, as you know, if you know anything about inverting the Laplacian, you start with a continuous function. The inverse Laplacian is not C2 like it should be, and so this actually fails, unfortunately. But morally it should work. So it's very close to working, and it's a slight annoying technical bit that it doesn't quite work in the space of continuous functions. It works in some Sobolev space or in some Holder space.
Is P part of your data or not?
P is not part of the data. It's invented by the fluid. So the fluid, it's essentially a Lagrange multiplier for a constrained system. And so the pressure is figured out by the fluid in order to maintain incompressibility. So the only data is the initial velocity field.
So in your differential equation, omega prime equals f of omega times omega. In the f of omega, there is p.
Right. So it's a very non-local function. So you shouldn't think of it's omega squared or something. It's it has to solve some differential equation on the entire domain, and then whatever solution it gets, then it sticks that. It's a function of functions defined in a pretty complicated way to get the
P is Laplacian inverse of that thing.
Yeah. So this is part of the system. So this data you know. The pressure figures out what it has to be in order to solve this Laplace equation, then gets stuck in here to the f. And so that's how f depends on the omega. Complicated way. Some green function. I will give a simpler example where it's a little easier to see explicitly what this looks like. The funny thing about this, if you read the original paper from Euler, it's really impressive considering he was just inventing it basically by himself. But one of the things he thought, especially since this was only the second PDE ever written down, was that he was just about to solve it. And so he sort of apologizes in the paper, like, oh, I'm sorry, because D'Alembert had solved the wave equation, a few years earlier. And so Euler's, of course, if anyone could do it, Euler could have done it. And he was thinking, yeah, probably in a few years I'll have the explicit solution. Unfortunately, I don't have that right now. And of course, 250 years later, we're still trying to figure out even the most basic things about it. But he made a promise that 2 years, I'll get you the full solution. So the strategy here is the Eben-Marsden technique, which is view the Euler equations as an ordinary differential equation on an infinite dimensional function space. And this, of course, came from the original idea of Arnold, although Arnold didn't really have in mind that this was going to be useful for proving theorems. It was more just for understanding the behavior. One of the funny things, so my advisor was David Eben, and the story he tells about this very famous work from 1970 is that everyone who worked with PDEs didn't believe this was possible, that you could not ever write a PDE as an ODE on an infinite dimensional space. And you could not ever use Picard iteration. And the only reason he did it was because he didn't know that. So he just started doing it, and it somehow worked by some miracle, but probably if he had actually known about PDEs, never would have even tried it. That's what he says. Okay, so what Euler actually did, so now I want to translate this into a PDE, which is the more familiar way that you know. So what Euler noticed is that if you're watching, so here's a trajectory x of y at time 1. Here's a later trajectory, time 2. and it's got some velocity, u of t1, u of t2. And so, of course, as this particle moves around in space, this velocity keeps changing, and so you're going to get complicated equations. But what Euler was thinking was, if you watch a river and you watch just one point, a bunch of particles flow through this, but there's a basic velocity, little u, of capital X and Y, little v of capital X and Y, and that's more likely to stay the same. So in a river, the velocity field, if you're looking at a single point and you watch the particles pass through that, that velocity stays the same more often. And so he thought he was going to get simpler equations if he did that, and that's where the introduction of this velocity field, little u and little v, comes in. Do some chain rule computations. I'll skip these two. But of course, you get this well-known version of 2D Euler equations in terms of the little velocities, little u and v, and the pressure function. And because everything was happening at the individual particle paths, you don't actually need these complicated functions, capital X and Y. All you need is little functions of little x and y. And so you think we've made things much simpler by ignoring the diffeomorphism gamma, capital X, capital Y, and just working in terms of these standard functions. Instead of a nonlinearity of composition, which, as you know, if you've studied this, the smoothness of group structures, it's very, very difficult. Ignore all the compositions, we just have quadratic nonlinearities. Supposed to make things easier. And incompressibility also becomes a much simpler constraint there in green. And even my pressure function Laplacian, again, removing the compositions. If I know the velocity field, little u and little v, then I know how to solve the pressure equation. So you've simplified quite a lot, but you have lost something really important. So you've gone from composition nonlinearities to just quadratic nonlinearities. But what you have is if you try to solve for ut and vt, then of course this right-hand side is not remotely a continuous function of the data you have, little u and little v. You have to take a derivative and you can't remove those derivatives. And so if you try to do things in a Banach space or a Hilbert space, where you have some nice theory, that will all fail because the right-hand side is just not a continuous function even, much less a locally Lipschitz function. Picard iteration does not work, and you have to actually invent PDE techniques to solve this equation. So that's kind of a problem. But like I said, this doesn't really work in the sense of inverting continuous functions, differential operators to stay in the space of continuous functions. I'm going to do a neater, cleaner example that works well in one dimension, so you can see how this is ideally supposed to work. This is the Kamasu-Holm equation written in 3 different ways. Kamasu-Holm equation is supposed to describe the evolution of water waves. It's kind of related to the KdV equation that Anton was talking about, but KdV doesn't allow for breaking of water waves, and some people think Kamasu-Holm is a better model because it allows for solutions that start off smooth and then may lead to a singularity. But I want to look at it from the point of view of diffeomorphism groups. And these formulas are going to get a little complicated, and I apologize in advance for that. It was easy to write them down. It was hard to take them out later. You know, editing is the worst part. I didn't edit this talk, so the formulas are nightmarish, but it gets better later. All right, so how do I invert this differential operator, a squared u minus uxx, which appears twice here? So there's a formula for inverting that, which looks like this in terms of exponentials. So I can invert, if I'm given omega, I can invert to find the velocity field u using this equation. And if I'm given whatever this stuff is, I can invert to find p explicitly. And what I notice here is I have some actual PDE behavior. I would like to turn it into an ODE by using the particle trajectories. And one thing I'm going to point out, because it's important later, is that there's a conservation law for the H1 energy. You can derive this the same way Anton showed you. Just differentiate this in time, plug in the equation, and watch it be 0.
physics question about the Thomas-Holm equation. You said like this is meant to describe water waves, but it's 1D, like the KdV equation. So do you mean like the wave is kind of constant in this direction?
Yeah. Yeah, so it's a very simplified model. It's you're assuming everything's basically just two-dimensional, and then you also remove the dimension going in. So it's really just supposed to be looking at a river from the side and only seeing the simplest possible approximation of the motion.
I see. And is this very trivial thing? If you know, like this thing is constant in this direction at time 0, then like this stays constant. Is this very trivial?
Who's to say what's trivial? The Euler equation's still not solved explicitly. Everything's kind of hard, but yeah, that's a thing you can derive without too much work. That if it doesn't depend on one of the variables, it will stay true for all time.
I see. Yeah, thanks a lot.
Okay, so my flow is some diffeomorphism, which just like the 2D Euler equation will be defined into the little velocity field. Some derivatives, and the important thing is this version of which is supposed to look like 2D Euler, becomes just a standard second order differential equation for the particle paths. And not really apologize anymore. I did once, and it'll get better. What I want you to notice about this is if I have everything happening inside some integrals, I can change variables inside the integrals, and the point of doing that is I remove compositions because I hate compositions. They're terrible for proving well-posedness. They're terrible for having continuous functions of continuous functions. It breaks all sorts of things. So every time I can remove a composition, I say I'm happy. And that's all I want you to notice here is I've removed the compositions by changing from capital Y to little y, and now I've got an equation for gamma. It depends on gamma t, depends on gamma ty, depends on gamma y, but no compositions. And if I differentiated this one more time with respect to x, what would I get? Still the same stuff, basically. So I don't have to keep differentiating to get a closed system. The system closes up after one step. Not after 0 steps, it's not closed right now, but if I take one more step, this is now a system for gamma, its time derivative, phi, which is its spatial derivative, v, which is the time and space derivative, and all I see here on the right side is that same stuff. No compositions, and so even though this looks complicated, you should think, if I've got a continuous function u here, and I square it, I have not only a continuous function of continuous functions, I have a smooth function of continuous functions. I can differentiate u goes to u squared as many times as I want, and it's perfectly smooth, even if u itself is not smooth. That's the funny thing that happens here. I don't need to work in the space C infinity. Work in continuous functions, still get a smooth vector field. So this is an ODE in some space of continuous functions. And what you can do with this, actual application, if you take an initial velocity, which is C1, and decays down to 0, and also has bounded H1 norm, then there's some time and a unique solution of the system, satisfying all the things it should. And in particular, when you change your variables back to little u, then you get a solution which depends continuously on the initial condition. So the funny thing is the dependence of this more correct data, gamma, phi, capital U, capital V, that's smooth. Smoothly depends on the initial condition. The velocity field that you thought you cared about does not depend smoothly. It has this awful composition. And I worked so hard to get rid of it. I need to put it back in at the end and it will break all this stuff, but I'll still get at least a nice existence theorem for this. And it may seem pretty trivial, except if I look at how anyone proves local existence theory for this PDE, they have to work in some, how do you prove existence for a PDE? You choose some function space, you try to choose the best one you can, and you hope that everything works out nicely. Maybe you do an approximation scheme and hope that it converges, but it all gets kind of complicated. Now this stuff is of course complicated, except you know how it's supposed to work. So the complications are just,
a list of things you have to check, but you don't have to invent any new technique. You just use Picard iteration as long as the things are working out nicely. So one of the things is, if I compare to other proofs of local existence, they have to work in some large Sobolev space, some Besov space, with various parameters. And these are considered very good results because you work in the lowest possible Sobolev space you can. But still, we get even better results because we work in the ideal space, which is continuously differentiable functions, which even your E- undergrad in an analysis class understands, as opposed to Sobolev spaces, which you need to be a grad student. So it's essentially the best possible space to get a result in. Right? And as soon as I break things a little bit, if I work in W1 infinity intersect H1 instead of C1 intersect H1, if I give up just that tiny little bit, the whole result fails. So it's the best possible result, and you only get it if you're thinking geometrically. So that's the advantage here of this approach. That's the only way I know, at least, to get optimal regularity for these PDEs is to actually think of them as ODEs. Okay, I'm going to say one other thing, just because this allows us to get more explicit solutions. If you're familiar with Euler equations, which you probably are, otherwise I probably wouldn't have invited you here. But if you're familiar with Euler equations, you know about the vorticity representation and using that to solve your equations. So this is the version of vorticity that works for Kamasa-Holm. Again, complicated formulas. But I want you to notice that if I use this equation, the omega, remember, is constructed from U as a differential operator. If I know omega, then I know U. I can reconstruct that, inverting a Laplace type equation. And so U is d gamma dt that can be reconstructed from omega. Omega is reconstructed from this in terms of just gamma itself, and I get a first order equation. Before I had a second order equation on the diffeomorphism group, 2-time derivatives. Now I only have a first order equation for my two functions, gamma and its spatial derivative phi. And again, a closed system. And again, no compositions. And so I can hope that it's a smooth function of all my variables, which it turns out to be. You can also see from this what can possibly go wrong. The only thing that can really go wrong to break this is that phi might go to 0, which is the spatial derivative of gamma, and we'll see that actually happening. Again, it's locally Lipschitz for any initial momentum. All you really need is omegas in L1, and again, you get a result in the optimal space C1 of diffeomorphisms. Now, to actually make it easier, let A go to 0, and you get an equation called Hunter-Saxton. In the periodic case, Lennels did this, a lot of analysis on this in 2007 and 8. In the non-periodic case, which is what I care about more, it's Bauer, Bruveris, and Peter. And also, Sarri and Saxton did some. The equation looked like this. It's the Liouville equation, if I differentiate it. So Liouville solved this in a 2-page paper in 1853. Fun paper to read, because the first page, it derives the solution. The second page derives the solution using an alternate method. Efficient paper. The solution looks like this. And what you can notice is that it, gamma x is supposed to be the derivative of a diffeomorphism. Diffeomorphism is supposed to have positive derivatives, so this doesn't. This can go to 0 in finite time. And when it goes to 0, the spatial derivative goes to -infinity. So it leaves the space C1, which I only expected local existence anyway. I'm not shocked that it leaves C1. It remains in H1 dot. So that's H1 without the lowest order term. So its L2 norm is preserved for this function, but its L infinity norm is not preserved, it actually goes to infinity. And it's one of the easiest examples to see the big difference between an H1 bound and a C1 bound. One of them stays bounded and the other goes to infinity. So this is why everything's difficult in this whole field. When you're trying to do local existence, you've got a Riemannian metric, which is giving you some energy. That is controlled. You've got a topology, and the lesson of all this is the correct topology is at least C1. You can't go any better than C1. But C1 is kind of far from whatever your Riemannian energy is telling you. And so finally, a picture. So here's what it looks like when a solution breaks down. This is supposed to be a diffeomorphism. It's getting flat. This is supposed to be phi. It's the x derivative, so that's going to 0. And then what does it look like in terms of the velocity field? It's a kink exactly like this. So that's a breakdown of your smooth solutions. And this is just repeating. So lesson is, things actually stay well behaved in terms of the diffeomorphism, can go badly in terms of the velocity field, because this is not the most natural way to think of things. Geometric way, more natural. Okay, so there's one situation where things become easy, and that is instead of an H1 metric, which generates Comassa-Holm, I will take an H2 metric. And essentially just view this for right now as same PDE I had before, but now omega in terms of U is a fourth order operator instead of the second order operator it was. If I do that, I will still get a nice, I won't write the formula, but there's some green function that will tell you how to get U from omega. And it all works nicely in C1 again. And you get conservation of energy, which is now conservation of the H2 norm. And the Sobolev embedding theorem says the C1 norm is bounded by the HS norm for any S, as long as S is larger than 3/2, which here it's 2, so of course that works. And so I get for free that U is controlled in C1. Nothing like this can possibly happen. And automatically, not only do I get local existence that works out nicely, but I get global existence for free. So this is the best possible situation when I'm working with diffeomorphism groups in the Banach context. I have a really nice, strong Riemannian metric that makes things behave like finite dimensions. And that's my whole goal here, to make everything behave like they're finite dimensional. So this is a sort of Goldilocks situation. The H2 is really good. The H1 is sort of in the middle, and the H0 is terrible. You'd think this is the easiest equation, the easiest one I've written down so far. It's the worst. Because if I try and put it in terms of Lagrangian flow, it is not an ODE. I am losing the derivative here, and I cannot compensate for it, no matter what I do. So here, not only do I not get global solutions, I don't even get local solutions. Nothing works in that case. And so the summary of all this is you get a situation where you can turn it into an ODE when k equals 1, local but not global. You can get global solutions for free when k equals 2, and when k equals 0, you get nothing. And so you can also interpolate in between when k is not an integer, see what happens there. And how you're supposed to imagine everything I say in this talk is, if k is high enough, then everything works out really nicely. If k is really low, then it doesn't. And gradually, some things start to work as you tune the parameter k up. And that's basically the entire theme. Halfway through the talk, and I probably should have said the theme at the beginning. I'll do better next time. So here's your basic non-integer values of k. The most popular ones are k equals 1/2 and k equals 3/2. When k equals 1/2, you get a Konstantin-Lax-Maida type equation, which is interesting. It's a nice model for 3D fluids, surprisingly. And when k equals 3/2, that was studied by Francois Guebamaz and Tudor Ratsiu as the equation that arises from universal Teichmuller theory. Notice k equals 3/2 is exactly the critical Sobolev index. You want to be greater than 3/2 to make things work nicely. If you're at 3/2, then things just barely work. And then all other k values in between are also interesting. Okay, so now the general framework here is we have a diffeomorphism group of some manifold, maybe a volume preserving diffeomorphism group. We have a Sobolev HK metric for some smoothness parameter k. I'm going to be specific and say the operator that gives you the metric is 1 minus Laplacian to the k, and the actual Riemannian metric is defined in terms of this operator. So it's HK. This is a 2k order operator, but it's only happening on one of the terms. A general framework. And the geodesics are given by the flow equation and the general Euler-Arnold equation, which you can compute in terms of brackets and integrating by parts and seeing what happens. So we've already seen this equation, so I won't go into more derivation of it. But basically, the omega is some differential operator in terms of u. That's the one-dimensional case, and higher dimensional cases are a little different. So you're hoping that this becomes an ODE in terms of the gamma, either as a second-order ODE or a first-order ODE if you use a conservation law. And so the rest of this talk is basically going to be all the things that I know about this, which is not very much, but the things I know that are proved and the things that are still open about this question of when I tune this parameter k, when do things become nice and finite dimensional? And so all that beginning stuff was just motivation for why that question's important. So the first question is, for which values of k is it true that the geodesic equation is smooth so that at least you'll get local existence of solutions? It's certainly false when k equals 0, like I showed you. It's probably also false for k less than 1/2, but I don't think anyone knows. I don't think there's a proof of that. So here's some partial answers. If
k is smaller than 1/2, then Sobolev embedding even to C0 fails.
Yes. Yeah, so I mean, that's why you'd expect everything to go really badly. But there isn't really a proof.
As far as I know, for anything in between 0 and 1/2. If k is a natural number, so one of the things I did with Gerard Misiowicz is for k at least 1, an integer, and you take the Sobolev HS topology for S pretty big, that is not close to the critical Sobolev index, that's not close to C1 where I want to be. 1 plus n over 2 is where I'd want to be. But if k is pretty large and the topology is also pretty large, then you can get this to work. Escher and Kolev in 2012 did the critical case k equals 1/2 in 1 dimension, again for fairly large Sobolev index. And then more generally in higher dimensions, surprisingly k equals 1/2 is still critical, this property. Again for now pretty close to the Sobolev index that gets you C1, but also you need to be fairly large if k is large. My letter is supposed to be there. But what we did in the C1 topology is what I showed you earlier. That's when k equals 1. So keeping everything pretty simple, but it gets you in the optimal situation. Then for this situation, which is nice and strong, k larger than 1 plus n over 2, that's what? Sobolev embedding tells you this will be enough to guarantee everything C1. And this is the case where all your results work out finally the way they're supposed to. But you need to have k pretty large to make that work. Nice thing is you can work in the correct topology, HK, where k matches the metric, but k needs to be very large. And then the most general result I know is for a general compact manifold, again at the critical case, k greater than or equal to 1/2, S still somewhat large. And then there's a recent result that we have, again, for very specific types of metrics, very specific space, then you can work in C1 again. So anything that's not on here, I mean, there are other things that you can do, but trying to get as close as you can to C1 is the sort of dream that you do as much as you can. On the volume preserving case, the most famous result that started all of this is Eben-Marsden 1970, which is k equals 0, S in the large enough Sobolev topology, then this all works for M compact. Scholar did pretty much the same thing for k equals 1, which is more complicated. And my former student Piers Washabaugh did this for k equals -1/2 in the 2-dimensional case. He used Holder spaces to derive a result for the SQG equation, another important equation in fluids. All right, so that's the local existence question. The global existence question, obviously more difficult and harder to accomplish. True less often. For which values of k does the Riemannian exponential map exist globally for all t? And let's assume that our initial data is as good as it can be, C infinity, to try and make things easier. C1 and C infinity are pretty much the same in this context. If your C1 fails, then your C infinity will certainly fail. If your C infinity fails, it's probably because the C1 is already failing. So there's not much difference here. But our partial answers here are, of course, for Kamasa-Holm, I showed you it's false. The global existence is false. You get solutions that look like this. For k equals 1/2, we proved that, based on Castro-Cordoba, we proved it's false in one dimension for k equals 1/2, which is the first time you hope local existence works, but global existence really fails. Li, Yu, and Zhai proved that in higher dimensions, the k equals 1 Kamasa-Holm type equation also breaks down in finite time. Escher-Kolev proved for strong metrics, k greater than 3/2 in dimension 1. As you expect, you do get global existence. Bruveris and Vialard in same result in higher dimensions. Things work out the way they should. I proved with Pierce that in the critical case, k equals 3/2, where you don't know, smooth solutions do actually remain. And finally, just recently, we proved that when k equals 2, the solutions break down. That's not quite good enough for 3 dimensions or higher. And the other cases, I don't know. Any k that's not integer or integer over 2, I have no idea. I mean, I'm pretty sure it's false, but I don't know how to prove it. If you take higher order Sobolev metrics and your Rn also increases, I think this is false. I think we have a proof, but it's not quite ready yet. But again, just for integer k. For non-integer k, I really don't know. Wide open. I think it's probably false if you're below the critical index. And at the critical index, I think it's true in 2 dimensions when it exactly matches. Sort of have a proof, which almost works. And I would conjecture it also works. It works in 1 dimension. It probably works in 2 dimensions. I would guess it works in all dimensions. On the volume preserving group, it's of course famously true in 2 dimensions for a standard fluid from Vladimir and some others back in the 30s, Gunter as well. Scholar proved it's also true for k equals 1. Of course, things get better as k increases always. So this is an easier proof than the original one. Probably true for all values of k, but I don't think anyone's studied this. The most famous unsolved problem in fluids is 3 dimensions, k equals 0, the L2 standard global existence problem for 3D Euler. Even for k equals 1, you'd think it would be easier. It's not easier. K equals 1, it's also unknown. Probably for k greater than or equal to 3, it's true for free because you have a strong metric. And another case, the one that Pierce studied, k equals -1/2, the SQG equation, also unknown at this point. And there's some other situations where it's... I'll talk a little bit about the linearized equations, the conjugate point situation. I guess not too much because I used up too much time. So essentially, if I now consider the question of stability, assume you know that geodesics exist for some amount of time. How far off can they be if you perturb them a little bit? So that's basically this question, and we've got some formulas for the linearized perturbations, which are Jacobi fields, and that's essentially what the Jacobi equation looks like, where this operator k is, by some miracle, happens to be constant and only depends on the initial condition. And you can compute this and see what happens, and that'll tell you the behavior of this equation, which will tell you the behavior of J, which is y composed with gamma, y is the adjoint of B. So essentially, can you solve this equation? The only time I know how to solve this equation is when gamma is a family of isometries, which will make this the identity, and then it's all constant coefficients. Operator equations, very trivial. The only time I know how to get an explicit solution. So finally, another picture. Here's what a Jacobi field looks like along a fluid. I've got a 2D fluid on the sphere. The sphere is not moving. This is the function on the sphere that describes the perturbations of a standard rotation. So I basically imagine there's a whole ocean on a planet. It's rotating like this. I throw some rocks at it. It gets perturbed, and the trajectories move around a little bit. A conjugate point happens when this thing comes back to where it started. So as Gabriel was talking about, a lot of the conjugate point situations talking about yesterday, kind of you'll see the same sorts of things here in fluids, and you have pictures in this way. So for 2D, I can see that as this thing moves, it eventually comes back exactly to where it started. That's a basic conjugate point. So the big distinction, we had heard yesterday about the difference between monoconjugate points and epiconjugate points for infinite dimensional operators. If your exponential map is Fredholm, then those are the same. If your exponential map is not Fredholm, then they're different. And the way you prove that this thing is Fredholm is if K0 happens to be a compact operator, then you get Fredholmness. And they have nice properties. And in this case, if the differential of the exponential map is Fredholm, then the conjugate points are the same no matter how you look at them. They're spaced out discretely. They're simple to understand. Maybe you can do CW complexes and topology on this space if your conjugate points are nice. And so that happens in 2D and not in 3D. So formulas. But essentially, again, tuning this parameter of smoothness K. If K is larger than 1/2 on the full diffeomorphism group, strictly larger than 1/2, then you'll get Fredholm. Greater than or equal to 1/2, you get local existence, but you need strictly larger to get nice behavior of this solution map. And again, that same thing happens. K equals -1/2 is critical for local existence. K strictly greater than -1/2 is critical for this Fredholm property. And the worst part is K equals 0 for a 3D fluid is exactly the interesting case. That's also exactly where it fails. So if you had any higher degree of smoothness in a fluid, things would be nice in terms of conjugate points. But in the real case of 3D fluids, they're bad. So yeah, smooth exponential map, but it's not Fredholm. So here are things I know about conjugate points. The original result of Eben Marsden, and one of the reasons you like to work on Banach manifolds instead of Frechet manifolds, is you can get an inverse function theorem, and the inverse function theorem tells you geodesics for short time will minimize, you will not reach singularities, at least have some amount of time you don't reach a singularity. So your geodesic will stay minimizing for a little while. And that's the original result. And then it took until 1993 until Gerard actually found examples of conjugate points along rotations on spheres. And then there are some situations where you guarantee they don't happen. Just recently, we've finished the classification of conjugate points that happen on the torus for a steady flow that's a Kolmogorov flow, which things with stream function that look like this. So basically, little rotations in cells on a torus. We classified all the ones that have conjugate points. If M and N are both positive, you'll get them. If one of them is 0, you won't get them. The most pathological example I know is S3 with the Hopf field. I can tell you the conjugate points happen like this. There are monoconjugate points. Exponential map is not 1-to-1. Monoconjugate points at all rational multiples of pi. Beyond pi itself, because remember, for a short time, that's minimizing. As soon as you reach pi, all the worst possible things you can imagine immediately happen. You get monoconjugate at all rational numbers and epiconjugate at all real numbers beyond pi. James Ben fairly recently proved that you get them also along non-steady solutions for Rossby-Harwitz waves, and Ali Suri, who was just here a couple days ago, essentially did the same sort of thing that we did for the torus, but did it for the sphere, and he already reported this result. I think this is the only case that's unknown. That's still open. But he worked it out for all the other ones.
Zero. Yeah.
For all of these, yes, thank you. These are all for the L2 metric, yes, H0.
And so this is for other metrics. On full diffeomorphism groups, I think you can ask me about this if you need to speed up. So anyway, there's the one thing I'll say here, which is surprisingly an open question. Kamasa Holm We know that solutions might break down or they might exist globally. We also know, we can work out the curvature, we think there should be lots of conjugate points. But it is unknown whether there's even a single conjugate point along a solution of the Komatsu-Helm equation, which is embarrassing that I don't know that. I tried to work, didn't try that hard, but I tried to work this out, I couldn't work it out. I'm embarrassed that even for the simplest model that I actually spent 15 minutes talking about, I don't know the answer to this most basic question. Is there a conjugate point that happens before a breakdown time for the Komatsu-Helm equation? And so these slides will be posted so you can actually see the questions as I post them, but I'm skipping some of this. The final thing, and I was just going to leave this out, but I remembered the title of my talk had curvature in it. I'm like, okay, I'll put some curvature into this. I did promise, and it seemed like a reasonable idea 3 months ago to talk about curvature. Here's what I know about curvature. So indirectly, curvature influences Jacobi fields. There are formulas for curvature that I'm not going to give. But for example, Arnold, who invented this approach to fluids, certainly, in 1966, one of the first things he did was work out the curvature using some formulas, see whether it's positive or negative, and use that to tell you whether you can predict the weather. If the curvature is negative, then geodesics spread apart. If geodesics spread apart, then when you make a small error, because you can't measure every aspect of the weather perfectly, when you make a small error, you'll get exponential divergence if you have negative curvature. If you have positive curvature, then it shouldn't matter when you make little mistakes. That was his original idea. And so he computed a bunch of these, probably thought that it was going to be negative all the time, but worked a little harder to find some directions where the curvature is also positive. So in general, it does take both signs. So most of these results are there situations where I can say the curvature is always negative or always positive? And maybe considering the general sectional curvature K of UV, maybe I'll hold U fixed and say, is it positive for all possible V? So along a fixed trajectory of the fluid, or the diffeomorphism, or whatever, along my fixed geodesic, are all possible variations governed by positive curvature and negative curvature. So here are the things I happen to know. If I want curvature to be positive for all V fixing a U, the only way I can do it, or even non-negative, the only way I can do it is with a killing field, so a rigid rotation that was originally shown. If you have a constant pressure, so if your fluid trajectories are all going in straight lines on the plane, maybe at different speeds, but all going in straight lines, then the curvature is less than or equal to 0 for all V. And then there are some other results where you can get a little bit better. It does happen fairly more often that you get non-positive curvature. It's still very rare to get non-negative curvature. Except in the axisymmetric case where surprisingly, like, we spent such a long time convinced we had made a mistake because I never believed this result. We found a condition in the axisymmetric case where you do get non-negative curvature operator. But in most cases, the curvature wants to take both signs. I think 2D fluids tend to have more negative curvature than 3D fluids, but that's, again, wide open. This is a thing I'd actually really like to study in the finite dimensional models that we have, like Zeitlin models that some people have talked about already. And finally, some results on sign of the curvature in other spaces. The only other one I know where it's positive is the horrible L2 metric on diff S1, positive curvature, unbounded, but positive. The only nice example is from Lennell's diff S1 mod rotations of S1, where you get actually a sphere, at least a portion of a sphere. That's the only time curvature is simple. Constant curvature, the only situation I know. Then there's some other situations, there's a higher dimensional version of that as well. For the H3 halves Vey-Peterson metric, I think they proved that the sectional curvature is always negative. I don't understand the proof. A wide open question that several people have tried really hard to work on, including me, and failed, is the H dot 1/2 metric. I think it's always positive. Cannot figure out how to prove it. I don't recommend you work on it. It broke our hearts. Barbara and I worked on it, couldn't get it to work. But be my guest. I'm just warning you. I think in general, h dot 1 is, should be simple, but I don't know. And then there's some results on the, okay, let's give up on the question of can I make the curvature positive always or negative always? Let's just say at least not too negative, or at least not too positive, so that results are at least close to finite dimensions. If I'm on a Lie group and it's finite dimensional, then of course, everything's bounded, all geodesics exist for all time, all this stuff works really nicely. So just asking that question, giving up on the sign, just asking is it bounded, surprisingly few results on this. So Gerhard proved using the H0, L2 metric, this curvature operator on HS functions, HS velocity fields, is an operator from U, V, and W, all in HS, to other HS vector fields. And he proved that's a bounded operator. And that's supposed to tell you, ideally, about growth of perturbations in the HS norm, in the strong norm. You might think there's a Rausch comparison theorem for that. There isn't. So what do I do with that? I know what to do with sectional curvature, but this is not sectional curvature. So the one other question that we've started addressing is this conjecture, working with Elise Lebrugant and Martin Bauer, just the simplest possible case I can think of, where you could try and establish whether this is true. What's the tuning parameter for K? In the simplest case of diff of the real line or diff S1, what it seems happens is, certainly for K less than 1/2, remember K equals 1/2 was the bare minimum to make anything work. When K is less than 1/2, certainly you can compute the curvatures unbounded. It's terrible. When K is between 1/2 and 1, if I hold U to be constant and really nice, make it smooth, and then see how it varies in V, then it seems like it's bounded, definitely unbounded if I let U and V both move. To prove it's unbounded, all you need is a single counterexample, so that's easy. And finally, you might think, and actually I still don't know if I believe this conjecture. Martin believes this conjecture. I don't know if I believe this. I still think K equals 3/2 might be the critical one. But he thinks K equals 1. I don't know. We're trying to figure that out right now. You know when K equals 1, then everything works. But between 1 and 3/2, if it failed, it would be a very weird example of things getting nice for a second at K equals 1 and then going bad again when you tune the parameter up. That doesn't ever happen to my knowledge, but it might, because it's infinite dimensions, who knows? Anyway, so that's a thing we're working on now. Anything that I haven't mentioned probably is a wide open problem. So a lot of this stuff I think would still be interesting for people to study. And so these slides will be posted, like I said. If you have any questions about what might be worth exploring, I would be happy to talk about any of that. Wide open otherwise. But that's it. Thanks to everyone for paying attention and for being here, and to the organizers. And if you went to the reception last night or to the reception last week and you didn't contribute some money to our organizers who are paying out of pocket.
Pony up. I know you have the money. Pay your organizers for this reception, which they pay for out of pocket. Thank you very much.